So proportional equations are they're lines. They're like the linear equations that you guys wrote equations of yesterday. Here's the only really difference between a regular equation of line and a proportional equation. A proportional equation is a linear function whose y-intercept is 0. That's it. Easy peasy. Your b value is 0. So if you have a line whose y-intercept is 0, if you have a line whose b value is 0, we don't simply call it a regular line. It's simply a proportional equation. So y equals 2x would be a proportional equation. Y equals negative 1/3 x would be a proportional equation. Graphically, if the y-intercept is 0, oh, wow, I can't draw a line. That means it goes through the origin. So that is a proportional equation. That would be a proportional equation once I move them down. So that's all a proportional equation is. If you have a line that goes through the origin, it is a proportional equation. Only equations that fit this model, y-intercept is 0 or graphically goes to the origin, are the x and y's proportional to each other. That is to say, whatever you do to one quantity, that same effect happens to the other. If you double one, the other doubles. If you triple one, the other triples. There is a particular way of writing these types of equations and setting them up. So here are the rules here. If we say that y varies directly, or another way we can say it is directly proportional. So those are sort of the trigger words there. Varies directly or directly proportional. Those are the key words. To x. Then we can write the following equation. So if someone says, hey, guess what? Y is directly proportional to x. If you were to translate that English sentence into math symbols, this is what it would look like. Y equals kx. For some real number k. So k is just a real number. It could be a 5, it could be a 3, it could be a negative 0.2. It doesn't matter. You can sort of think of, well, actually, it does matter. It just can't be 0. Right? That's important. Because if it equals 0, we don't have a proportion because anything times 0 is 0. Okay. You can sort of think of k as the slope, but since we're talking about proportional equations, it just gets its own special name. K is called the constant of proportionality. Right. So constant of proportionality is a vocab word. So every single proportional equation will have some sort of constant k. If I say two things vary directly, y varies directly to x, you just set them equal to each other. Y equals x, but you got to put the proportionality constant k there. So that's one way two variables can relate to each other. They can vary directly. Another way that they can relate, if we say that y varies inversely, slash, another way we can say that is inversely proportional. So those are the key trigger words. Varies inversely or inversely proportional. 2x, then we can write the following equation. Y equals k. So in any proportional problem, it always starts off the same. Y equals k. So if you have no idea what to do and it's a proportional equation, you can always do y equals k. But if it varies inversely, you put the second variable in the denominator. So that's sort of the key idea. Things that vary directly, the variables go in the numerator. Things that vary inversely go in the denominator. K is the constant proportionality, of course. Easy peasy, that's not too hard, right? Varies directly, goes on top. Varies inversely, goes in the denominator. Now, I sort of separated these as two separate proportions. There's no law that says one variable has to be proportional to just one other variable. You can have one variable be proportional to 2 different variables, 3 different variables, 4 different variables. You can chain them up as many number as you want. If you do have multiple proportionalities, you may hear or read the word jointly proportional. If you hear that phrase, don't get freaked out. That simply means more than one proportion. Right? So, y is jointly proportional to x and z. That just means you have 2 proportionalities instead of 1. Let's take a look at some examples here. And as luck would have it, they are your favorite. They're all word problems. During a thunderstorm, you see lightning before you hear the thunder. That is true. So next time we have a thunderstorm, just run outside in the middle of the street and just listen. Yes. Hopefully you're not holding anything metallic in your hands. Your phone would be a good conductor because light travels much faster than sound. So if you've never taken physics, that is true. Light travels a heck of a lot faster than sound does. The distance between you and the storm varies directly as the time interval between the lightning and the thunder. Letter A. Suppose the thunder from a storm that is 5,400 feet away takes 5 seconds to reach you. Use this information to come up with the proportional equation. It's a lot of writing, so I'm abbreviating. Proportional EQ is equation. Now, when it comes to these proportional problems, this is very stereotypical. They'll give you the varies proportionally, varies inversely, and then they'll give you some numerical information for you to plug in and solve. If I ever ask you, hey, come up with a proportional equation, your job is to figure out the k. That's what makes proportional equations unique from one another. K separates, just like with regular lines, different slopes represents different lines, bless you. Different constant proportionalities represents different proportions. So we have to find it. So the first thing you want to do is you want to read the problem and look for those trigger words. Varies directly, varies inversely, inversely proportional, directly proportional. And I hope we can find that the trigger word is right here. Varies directly, right? Next, we have to figure out what is varying with what. It's usually going to be before the trigger word and then after the trigger word. So what does this trigger word connect? It connects the distance between you and the storm with time interval between lightning and the thunder, right? So those are the two quantities that are varying: the distance between you and the storm and the time interval between hearing the thunder and seeing the lightning. You know, that's a lot of writing. The blue and the orange, I'm going to call it orange. So let's use variables, shall we? To make things simple. So let's let G, what variable should we use for the distance between you and the storm? What variable should we use to represent the distance between you and the storm? How about D for distance? Makes sense. So I'm going to let D equals the distance between you and the storm. Now I need a variable for the orange, the time interval between the lightning and the thunder. Gee, what would be a smart variable to use? T. Let's let T be the time interval between lightning and thunder. So once you have your variables defined, we can finally write the equation. Now remember the, I'm going to scroll up, but I'll scroll back down. Remember these rules here. That's how you set up these problems. Anything that's varying directly will go in the numerator. Anything that's very inversely will go in the denominator. So this problem says the blue varies directly with the orange. So I'm going to start with blue, distance, equals K. You always start proportional problem by equaling K. Every single proportional problem will have equal K. And then since it varies directly, I'm going to put the orange in the numerator. Voila. There is our proportional model. It's not our equation yet because we don't have any numbers. We need to solve for K. Once you have the model set up, now is the time to start plugging in information. Well, what information did they give us? They gave us 5,400 feet. 5 seconds to reach you. I hope it doesn't take a lot of thinking to know that the 54 feet away is the distance between you and the storm. I hope it doesn't take a lot of thinking to say that the 5 seconds for the thunder to reach you is the time. Everyone okay with that? Just plug it in. So D is 5,400 equals K. T is 5. And what do you know? You have an equation to solve for K. Divide both sides by 5, and then you're home free. So K equals 1080. A common mistake students make is they stop right there. They say, okay, I solved something. That's my answer. But the question says, come up with a proportional equation. So all you have to do is take this K and put it back inside the model. So my answer is D equals 1080T. That's the answer. That is the full proportional equation. Okay. Not too bad, right? Say that again?
Is that going to get harder?
The only way I can make this harder is if I throw in more proportions. It's proportional to T, X, and Y, so on and so forth. But it's the same logic. Anything that's directly proportional is on top. Anything inversely proportional is in the denominator. This question did have a part B to it. If the time interval between lightning and thunder, I'm getting lazy, L and T, is now 8 seconds, how far away is the storm? Right. This would be a hard question to answer. We're not weather people. We're not meteorologists. How the heck are we supposed to answer this question? Well, fortunately, in part A, we came up with an equation. So that is a valid equation to use. We have an equation that uses time. Just plug in the time in. So from part A, we know that this is true. So then we can just plug in the 8 seconds in for D. So that's 1080 times 8. So that is 8640, and the units in the problem was feet. Okay. So if you hear a storm in this particular problem, if you hear a storm 8 seconds in between thunder and lightning, it's about 8,640 feet away from you. And this, by the way, this is how storm trackers really work. They measure the distances between lightning and thunder, do some calculations. They can calculate how far a storm is. Yep. The comment that was made in this example is that it? Does it get any harder than that? Only way it can really get harder is if you throw in lots of different variables. But you just have to be consistent. Anything that's direct is on top. Anything that's inverse is on the bottom. So let's take a look at this example here. The apparent brightness, and they're going to give you the variable capital B of a light source. Right. Could be a light bulb, it could be a flashlight, whatever. And the units for apparent brightness is watts per meter squared. So capital W is a watts per meter squared, is directly proportional to the luminosity, which the variable we use is capital L, and his units is in watts of the light source and inversely proportional to the square of the distance, and they tell you use the variable d, lowercase d, from the light source. And the units there will be meters. Write a proportional equation that describes this variation. So, I mean, that's the only way these problems can get, quote, harder, is if you have more than two things relating to each other. Now, the first thing I would do is try to figure out what pieces, what players are involved in the story and put variables to them. But this question was nice. It sort of did that for us. I hope everyone can just see that we have apparent brightness as one variable, luminosity as another variable, and distance d as another three variables. So you guys agree that this problem has three different variables in it. Next thing I want to do is I want to sort of highlight or figure out where are my trigger words, inversely proportional, directly proportional, so on and so forth. In this problem, we have two trigger words. We have directly proportional and inversely proportional. So you have to figure out which variable is doing what. Now, fortunately, it reads like an English sentence. Whatever you read first is what comes first. So if we break this down, what do we have here? We have the apparent brightness B is directly proportional to the luminosity. I just read that straight up as from start to finish. You guys can agree with that. Apparent brightness directly proportional to the luminosity. So we're going to write that. Apparent brightness B is directly proportional. The moment they give me proportion, equals K. Always equals K for proportion. Well, it's directly proportional to the luminosity L. Directly proportional. Will that be on the top or on the bottom? Top. Directly proportional will be on top. But if you continue reading, it also says it's inversely proportional to distance. So I got to put the letter D into my equation. Well, since it's inversely proportional, will be on top or bottom? On the bottom. Now it also says, and I'm going to highlight this, the square of the distance. So I'm not just going to put a D down here. It says it's the square of the D, so it's D squared. That is the equation. Easy peasy. We're done. I don't have to solve for K because they didn't give me any numbers, so there's nothing to solve. Yeah. All it is basically, can you read a sentence and translate it? That's what this lesson's all about. But once you have the equation, you can answer questions like this. Letter B. If distance is doubled, by what factor will brightness change? And this is a very stereotypical question to ask when it comes to proportion. Once you have a proportion, they'll usually ask, hey, I'm going to double this guy. I'm going to triple this guy. I'm going to take 1/2 of this guy. How does it affect the rest of the equation? The technique is to always compare it to the original. So you have to remember, the original is B equals KL over D squared. Right? Just keep that in mind. Now in letter B, what changes are we implementing? What changes are we doing according to the problem? If what is doubled? Distance. Now mathematically, if my original distance is D, mathematically, how do I write that D has doubled? 2D. Everyone okay with it's being 2D? So what you're going to do is you're going to take the equation, but you're going to change the D into 2D. You're going to change it into whatever they tell you to do. So here's our change. And here's my suggestion. Whenever you do a substitution, always use parentheses. So I did not change the B, I did not change the K, I did not change the L over. I changed the D into a 2D, and since I'm doing a change, I'm going to use parentheses. All I did was I changed the letter D and substituting a 2D. We're okay with that. Then the rest is just math. All right, okay, so that's equals, and I'm going to put a prime here, B prime, just to say that's different, because you might get confused with this B with this B. So I'm going to use a prime up here just to indicate that it's different. So that's what? KL over, what's 2D squared? 2D times 2D is 4D squared. Now let's take a look at the original here. And I'm going to sort of like highlight it by writing it in a different color. B equals KL over D squared. What your goal is, once you do this change, is to look at your final result. Here's our final result. Can you guys spot the original expression? I'm going to highlight the original expression. The original expression was KLD squared. So in my final result, wherever there's a KLD squared, I'm going to highlight him. You guys okay with that? Well, according to the original, what does KL over D squared equals? The original B. So this equals, so all this guy here equals the original B. So now we can answer the question. Here's the new brightness. How did doubling the distance affect the apparent brightness? How does the new brightness compare to the old brightness? It is what? 1/4 the original, right? So that's the answer to the question. By what factor will the brightness change? The brightness changed by a factor of 1/4, right? So to answer these types of questions, hey, you have a proportion equation. Now go ahead and change parts of it by doubling here, tripling here, taking 1/2 of it here. All you got to do is just do that substitution, get your final result, and compare it with the original statement. Guys okay with that? Let's just do one more with the same equation. One more change. If distance is cut in half and luminosity is tripled, by what factor will the brightness change? Again, keep in mind the original up here. So let's do the change. I'm going to do B prime because it's the new brightness equals, and all I'm going to do is substitute the changes that they tell me. So the changes that they tell me is distance is cut in half and luminosity is tripled. Hopefully everyone agrees that distance is cut in half is 1/2 D. Tripling the luminosity is 3L. So then do those substitutions. K 3L over 1/2 D squared. And then all you got to do is just do math. This is 3KL over 1/2 D squared is 1/4 D squared. Do you remember what our elementary school teacher said? If you divide by a fraction, multiply by the flip, multiply by the reciprocal. So dividing by 1/4 is the same thing as multiplying by a 4, so that becomes a 12KL over D squared. What I'm going to do is I'm going to highlight the original, and here was the original here, KLD squared. So that's 12 KL over D squared. And remember that the original equals the B. So now we can answer the question. How does the new brightness compare to the old brightness once we make these changes? It is 12 times brighter. That's what it literally says. It's 12B. It's 12 times brighter. The brightness changed by a factor of 12. Yep. Don't just put 12B. If you put this as an answer, that means nothing to me. Write a quick sentence. So proportional equations, very, very simple and straightforward. There's only two types of proportions that we'll talk about in this class. Are things directly proportional or are they inversely proportional? If they're directly proportional, you put the variables in the numerator. If they're inversely proportional, you put the variables in the denominator. There's always a k somewhere involved. Put the information that they give you, solve for what they ask you. That's it. That is, I forget, was this 2-6? Yeah. That is 2-6.